Hello everyone. On behalf of my co-author Karsten, Walther, myself, and on behalf of Perinet company, I would like to welcome you to my presentation of our paper, Realizing Seamless Integration of Sensors and Actuators into the IoT. We all know that the internet has been a huge success, which is mainly due to its hourglass architecture. On the bottom, we have a lot of different technologies, which are all unified by IP. And then above IP, we have a lot of different protocols and applications. Nowadays, we are no longer talking about the internet itself. We are talking about the Internet of Things and industrial Internet of Things. And we can find this in a lot of different applications. For example, in home and building automation, we want everything to be controllable by the cloud or from the cloud. We have switches and routers, we have Wi-Fi, we might have intelligent light bulbs and digital assistants for voice control, but we also have standard control entities or devices, and we have sensors and actuators, maybe a camera, maybe a temperature sensor, heating control, etc. On the industry side, it's a little bit different. Usually we don't want everything up in the cloud. In some cases we do. We also have switches and routers, and we have control devices. These control devices can, for example, be the SPSs. And then we have also sensors and actuators connected to these SPSs. Now, when I'm talking about seamless integration, what is the problem? Well, the problem is that at the moment it is not seamless. When you look at current installments, you find that IP is going through a lot of devices down to the control devices. But the sensors and actuators very often, with the exception of IP cameras, are not IP based. They are not network capable. This means for the industry example that the sensors are connected to an SPS and need to be addressed by talking to the SPS and asking it to poll the values of whatever is connected to a certain port of this SPS, which is not really what we want to do. I mean, in some installments, this has worked for years, but looking to the future, it would be much easier to make the sensors and actuators themselves network capable and talk to them directly. In the next slides, I will explain a little bit more why this would be better. First of all, when you look at typical industrial appliances, then you find that process management, operations management, and corporate management level are completely IT based almost everywhere. So you have IP at the top and down a few layers. But the closer you get to the actual production line, you find that things become less IT based, or there are more systems that are not IP based. So when you get down to the field bus area, you get a semantical gap because process management, operations management, and corporate management level cannot talk to them directly. Second of all, most of these installments are realized in a centralized manner. The sensors and actuators do not have any intelligence of their own. They just deliver the sensor data to a central decider. The central decider decides whatever should be done and transmits back some configuration data or some orders to sensors and actuators. This means we have a lot of network traffic and we have high computational load at the central decider, which becomes a single point of failure. Therefore, these approaches do not scale well. Third, when you look at these applications, they are often control loops and have real-time requirements. Real-time requirements means that we do not only have functional properties, of course we want the results to be correct, but we also need them in a timely manner. Runtime, latency, and jitter play a big role. If we now increase the network size because we want to add more elements, this means we increase latency. Also, this means we increase network load, and increased network load means that jitter is harder to predict because, well, the network might get saturated. And these two together mean that the end-to-end runtime also increases. And we don't want this either. And to conclude the motivation, installment and maintenance are complex. Many of these sensors supply only analogous data or maybe bit fields. And as I told you before, they can only be addressed by the port of the machine they are attached to. This means that when we install them, we need to track which port at which machine they are attached to and tell this to the higher levels so they can interact with them. Also, maintenance is not easy because we need to find out where they are located, and if we want to rearrange things, for example, one of the ports does not work anymore, the sensor is fine. We move the sensor to a different SPS, to a different port, and now we have to inform all of the upper layers where it is now located. Even though they don't care, they just want to talk to the same sensor in the same way they want before. So all of this shows that what we really want is seamless networking. We want all of the sensors and actuators included in our IP-based communication. Let me show you how this would solve the problems described above. First of all, when sensors and actuators have their own IP addresses, they can be directly accessed using HTTP. Network-capable sensors mean that direct communication from process management, operations management level, corporate management level, and so on is now possible, which means the semantic gap I have mentioned earlier has now been removed. Another opportunity that arises now is that we can design systems from top to bottom instead of focusing on the field bus and then working our way up. This was necessary in the past because we had to make sure that the field bus elements were reachable. Now we know that they will be reachable, we only need to know the IP addresses under which they will be reachable. For the network and processing load, we have a reduction. Of course, we have the same application. This means the same amount of data is produced. However, it is no longer transmitted in raw format. We can, for example, if we know that certain thresholds are interesting, just transmit a binary information. Has the threshold been exceeded or not? This further reduces the size. And we can go even one step further. If we know which data is of interest, then we can only transmit data if the threshold has been exceeded. So we turn our system into an alarm system. We only send messages with already pre-processed data if changes have occurred and some action is necessary. The next thing we can include is direct communication between sensors and actuators. When we have intelligence not only in the sensors but also in the actuators, we can communicate from sensors directly to actuators. Sensors will know which actuators are interested in their values, and if an actuator needs 2 or more different sensors to decide what it has to do, well, then it just combines these values from the sensors once it receives them and does a local sensor fusion. This means we have only local communication, as usually the actuators that need to react to certain sensors are close to them. This leads to a further reduction of network load and of course to reduced latency because we don't have to communicate from the sensors to the central decider and back to the actuators instead of staying in the local neighborhood. The central decider can be removed. For some reason we might want to keep it in order to do some tracking, but theoretically it can be completely removed, removing the single point of failure. In reality, we would probably keep it as a logger, but if it fails, this means we lose some logging information, but the plant can still continue working. And the fourth thing is we now have unique location-independent identities for our sensors and actuators. They are no longer depending on the port and the machine they are attached to. They have complete independence from location, which means we have easy installation, configuration, and migration. We can move them from one machine to the next without them losing their IP address and therefore their identity. Also, they are easily replaceable and reconfigurable at runtime. And we have another benefit: we can use better security. When our sensors and actuators are accessible using IP, we can use state-of-the-art encryption protocols like TLS. This even enables us to have virtual private networks within our factory. This is actually a huge problem in industry nowadays, that different machines from different vendors can access each other's data. With our solution, they cannot. While IP-based sensors and actuators solve the problems I described earlier, there were a few challenges we ran into when trying to realize them. I brought a selected few of them to you today. First of all, there was no standardized cabling and connectors for IP-based sensors and actuators. Luckily, this changed in 2020 with the appearance of IEC 63171-6. As a user interface, we wanted to use a web browser. Why? Well, a lot of different automation solutions come with their own configuration tools and different user interfaces. This means the users have to learn to work with them. However, everybody knows how their web browser works, which was why we decided to use a web browser as user interface. For this device discovery, we decided that for security reasons, we don't want global IP addresses, even though IPv6 supplies enough of those to give each and every node one of their own. Instead, we wanted them to be visible only in the local networks, therefore increasing security. Therefore, we needed link local addresses. Name translation is then necessary, but this is not limited to .local, which means that in some cases, in some browsers, we have really high delays, and if these are combined with low timeouts, our devices were not found even though they were connected correctly. In other examples, some browsers still prefer IPv4 over IPv6. There is an example where the browser does an initial test whether it is connected to the internet with IPv6. If it is not, it completely switches to IPv4 mode and ignores everything that is connected via IPv6, even if it is connected locally. Interestingly, there are standards which are solving these issues, but today's browsers are not compliant to these standards. There also was an IETF working group, ZeroConf, which wanted to solve these issues, but the group was dissolved without reaching an agreement. Despite these challenges and more, we were successful. We designed and built the Pericore SPE, the first module worldwide that enables the integration of sensors and actuators into single-pair Ethernet. You can see it here on the right-hand side. It is about the size of a Eurocent. This module can be used for direct integration into sensors and actuators and supplies them with an IP address and makes them directly accessible via web browser. However, we are of course aware that there are a lot of sensors and actuators already in the field which are not network capable. Therefore, we included our Pericore into a Perinode. Perinode is essentially an adapter which can be used to retrofit existing sensors and actuators with network capabilities. Here you can see an example setup. We have a distance sensor, we have a temperature sensor on the right. Each of these has a Perinode that is connected to them, making them network capable. These two Perinodes are connected via Peri lines, which are single pair Ethernet cables, to a Peri switch, and from there with another Peri line to a Perimica. And this Perimica can be plugged directly into your standard Ethernet. With these, the transition is complete. You can see here on the left side the old network we had where IP was only available in the top layers. Then below this we had, for example, SPSs, and then down on the way to the sensors we had switches, AD, converters, etc. until we reached the sensors that were probably largely analogous. On the right side you see the new variant. We have the AD converter directly attached to the previously analogous sensors. We have within the Perinode the availability of IP addresses and network stacks for the nodes, so we can access each and every sensor and actuator directly using IP, and we can use state-of-the-art security protocols like TLS. With this, I would like to close my presentation. I thank you for your attention, and I would be delighted to answer any questions. Thank you.